Hello, Jean-Michel.
Hey, sorry for I had to reconnect.
Good to see you. Okay, as I said, we didn't pre-record this video. Normally, we are pre-recording videos in order to exclude technical line issues. So it's a good reason to pre-record. In this case, we didn't because of the shortness of time. And we're doing this live, so I hope the connection will stay there. And let's just start with your talk. Jean-Michel, the stage is yours.
Thank you very much for the introduction. So I will be discussing about time of flight measurement with subsampling period resolution. This is a work we did with my colleague Gwenaël Goavec. Actually, it's a side effect of our ongoing work on two-way time transfer using satellite link and a general interest on software-defined radio, radar, and basically anything that is related to time. So what's the story here? The story is that usually when you learn about, on the next slide, when you, in the introduction, you learn at school that when you're sampling a signal at a sampling frequency fs, then your time interval between two measurements is 1/fs. And this time resolution basically drives the whole signal processing, since once the A to D converter has recorded the data, whatever the time interval in the processing, subsequent processing step will not matter anymore, because each sample has been timestamped every TS sampling period. And this you can find in the radar range resolution, where the range delta R is the velocity of light, c, divided by twice the bandwidth, twice because it's a two-way time of flight for monostatic radar. And the bandwidth in the radio frequency band drives the sampling frequency in the baseband once you've done the transposition. So are we limited in this time of flight measurement to TS, the sampling period? If we look at the next slide, we will see some simple simulation. This is just, I put a few lines of MATLAB code to show you how I simulate this. So I take some random data and I spread some information by convolution. So I just spread out the information over the adjacent 30 samples by convolution. And then I move the data by 1, 2, 3, 4, up to 6 sample offset once every 10. So basically, I decimate by 1/10, but because I've spread the information by convolution, I have some information on the adjacent sample. And what you see, if you were just to simply look at the maximum of a correlation, you would always find 0, because the autocorrelation of a random signal is maximum at time lag 0, and that would be it. But you see on the magnified version on the right that actually maybe we can learn something more from the shape of a correlation peak. And that's the core story here. Under the assumption that you're not looking at a one-to-one relation between the time domain and Fourier domain, but actually that you have some knowledge that there's a single correlation peak, we can make some super resolution measurements. So in this case, what you see is that the shape of a correlation peak will give us some information on the fine resolution of a time of flight. On the next slide, I am showing you some example where I'm using this. So we saw together a few presentations about time of flight measurement of ionosphere. This is my measurements from Besançon, located about 400 kilometers from from the DCF-77 emitter in Germany. And I'm recording the time of flight. You see, I've been doing this since 2017, end of 2016. And this is reference to GPS. So actually my sound card is a 2 sound card input. One channel is looking at the 1 PPS from GPS, the other one from DCF-77, and I look at the time of flight. Now, DCF-77 since 1988 has been you've got two signals, the AM that everyone knows of, and they added in 1988 this phase modulation on the bottom left of the slide. This is a 645 hertz, or let's say 700 hertz. And if you were just to take the inverse of 700 hertz, you would think, well, I can measure DCF77 with something like 1.5 millisecond resolution. And yet on the chart on the right, you do see that we have something like plus or minus 200 microseconds. And actually, if on the next slide you looked at the zoomed in version, which is just 1 month, you actually see that most of this fluctuation is actually daylight fluctuations when when the sun is rising and setting, and you have this ionosphere motion. So actually, what we did, we measured something like 10 microsecond timing resolution on this signal, and that allows us. This is allowed by this super resolution technique of fitting the cross correlation, the correlation peak. So now on the next slide, I would like to show the outline of the experiment that we're doing. The objective on the right of this slide is to calibrate or to characterize the time delay between dual channel coherent receivers. So say the Etus Research X310, the Etus Research B210, or the XTRX, the difference being that the X310 is a baseband receiver with the FPGA directly connected to the A2D, directly connected to the input. The B210 has the fancy AD9361 front end, and the XTRX is a Line Microsystem LMS 7002. Now, in order to spread the information and do this fine measurement, what you do need is to try to spread the time information over many samples. And to do this, you need something that doesn't repeat. Otherwise, you would not be able to differentiate one sample from the one further away. So you do this by generating a pseudo-random sequence. And in this case, Gwen programmed this FPGA at the middle of the chart with a pseudo-random sequence generator. In our case, we randomly selected a 100 kilosample long code, which is run at 2.5 megahertz. So 2.5 megahertz BPSK code will occupy a bandwidth of 5 megahertz, which is the sampling rate of our SDRs. And so you would expect at 5 megasample per second that we will have a time interval or time sampling period of 200 nanoseconds. And can we do anything better than 200 nanosecond accuracy between the two channels of the dual channel SDR? So to characterize this, the FPGA outputs the baseband signal at an intermediate frequency of 70 megahertz, so just toggling the GPIO, running the PRN sequence over a phase modulation, a binary phase modulation. We filter out unwanted spectral component using a surface acoustic wave filter centered on the space communication intermediate frequency 70 megahertz. We split the output and feed using same cable length inputs A and input B. On the bottom, you see the very simple GNU radio chart, which is a USRP source, external clock, external PPS, because maybe with external information, we can synchronize multiple receivers. And on the right, you will have, for example, 2x310. So you duplicate the two information if you want to multiply. Everything is dumped simply to a file sync that will allow us for post-processing of this information. On the next slide, you have this outline of the experimental setup. So the B210 on the top, the X310 on the right, on the bottom of the B210, with the splitters on the left. Be aware that while the B210 allows for large amplification, the X310 requires something like 6 dBm for operating full scale, hence the amplifier on the bottom chain, and on the background you see the FPGA running the pseudo-random sequence. I would like to emphasize, as Daniel has been talking about Amaranth, that the whole development is portable to multiple FPGAs, and you can find on the GitHub on the left of this slide the repository where the BPSK, QPSK pseudo-random sequence modulators are implemented. So on the next slide, our first measurement. The first question was, can we just run the FPGA code into the X310 or the B210 and say, well, there is a 1 PPS that gives you the time. You've got the 10 megahertz that gives you the frequency. So maybe the X310 is clever enough to align its sequence if you set the external PPS. And what you see on the right are a few hundred measurements. These are the different curves. In the x-axis, you've got the measurement, each sequence of measurement with 40 millisecond per code. So for 250 measurements, that would be about 10 seconds worth of recording. And what you see is that from one measurement to the other, so within each measurement, we have a standard deviation of about 6 picoseconds for B210, something like 37 picoseconds in this case for low SNR. You'll see that we added later the amplifier to get a full-scale measurement of the A to D converter. So within each trace, we are well better than the 200 nanosecond period, but from one measurement to the other, you see that we're jumping 40, 50, 70, 90 nanoseconds. So we're basically any place randomly in the sampling period. So the PPS basically is sampled before the A to D clock and not after, meaning that there is no alignment of the A to D converter over the PPS. However, on the next slide, we will see that within each dual channel measurement differential channel. So this next slide shows the differential measurement between the two B210 inputs. And here you see that multiple measurements actually do lock to within. So if you look at the y-axis, nanoseconds, we're going from 0.32, so that's 320 picoseconds, up to 220 picoseconds. So now we have max to minimum of 100 picoseconds. So you see that it works because we do qualify the time delay between the two channels of a B210 to be in the 100 picosecond range. Within each measurement, we have something like 40 picosecond fluctuations. And that tells you that the B210 is indeed has coherent dual channel if you reference one channel with respect to the other. Now, in the project we're working on, we are asked to achieve sub 100 picosecond time resolution. So the B210 is at the limit. And of course, with the very fancy, complex AD93 something front end, well, we have no idea what's happening there. Analog device knows, but we have no clue about what is happening to our samples. So now on the next slide, we are going to consider the same experiment, but an X310. So the X310 is just A to D converters feeding the FPGA and recording the data over Ethernet. And what you see now is that the delay between, again, one channel versus the other is very concentrated. If you look on the left, you've got the statistics, something like maximum minus minimum between the two channels of sub 10 picosecond. Now, the other interesting thing that you might think of is, okay, he's claiming that he can measure time of flight with sub 10 picosecond resolution. What if I add some length, some delay between one cable and the other, which is what we did between the top and the bottom chart. If you look closely on the top chart, the curves are centered on something like 90 picoseconds, 0.09 nanosecond. On the bottom, we have 15 picoseconds, 0.0515 nanosecond. So 90 minus 15 is about 75 picosecond time delay. And what is 75 picosecond time delay? If you'd say that in a coaxial cable, the speed of light is 60% of the speed in vacuum, that is 20 centimeter per nanosecond. Well, 75 picosecond is 1.5 centimeter of coax cable. And if you look at the geometry of an SMA connector as the one we use, well, you've got two lengths of about 77 millimeters, which add up as something like 14 millimeters. So I think we can reasonably claim that we do measure with sub 10 picosecond time delays between our measurements. This is all done by referencing every clock on ultra-stable clock source, hydrogen maser. So the FPGA, the software-defined radio, everything is clocked on a hydrogen maser. Indeed, on the next slide, we're going to consider what happens if we are measuring not on the hydrogen maser. The FPGA must be clocked on the high stability time frequency reference, which is hydrogen maser. But now, what happens if a radio, software-defined radio, is running on its internal oscillator? It's a temperature-controlled crystal oscillator. And what you see is on the top right chart, on purpose, I have offset one of the curves by 10 nanoseconds with respect to the other. Otherwise, they would perfectly overlap. So you do have a drift because the TCXO is not a high stability atomic clock. It's just a quartz oscillator. So its frequency is off with respect to the high quality reference. But because we're doing a reference measurement, well, the common mode is rejected. And actually on the bottom right chart, when you measure one channel with respect to the other, the top chart is just one channel and the other channel. On the bottom chart, you see that the difference is as good as we had when we were clocking the X310 on the hydrogen maser, with maximum minus minimum of the time delays in about 1.7 picoseconds. So that tells you that you actually don't need to run the SDR on the high stable clock if you wish to do this kind of measurement. You just need to have a reference which is fed with this high quality signal. So now that we are confident that a single SDR has two channels that are consistent, on the next slide, we're going to consider what happens with multiple SDRs. For example, the X310 provides the ability to cascade the receivers. Now, if you just cascade the receivers, we already saw that 1 PPS and 10 megahertz is not enough to synchronize the two channels. And again, on the right, on the full right light blue chart, you see that the time delays are distributed randomly. Now we have 4 measurements because we put 2 X310. Each X310 fitted with 2 receivers, and the time delays between these channels is random between 0 and 100 nanoseconds, so randomly spread in a sampling period. Now, if we look on the middle chart, we see what is happening between channel 1 and channel 2 of a first X310, that's the blue curve, channel 1 and channel 2 of a second X310, that's the red curve. We already knew that they were coherent, but now what we're doing is we are spreading the same signal, the same reference signal, to also compare what is happening inside each X310 with respect to the other, that's the green curve. And each one of these curves is quite thick because the measurement is repeated 1,000 times. So actually, the thickness of a curve is the distribution of the time delay in blue within one X310, in red within the two channels of the other X310, and in green between the two X310. And we do see again, although the result is slightly degraded, on the right I put the number. So we go from a fraction of a picosecond to 1.6 picosecond between the two X310, but we do have well below sampling period synchronization between the channels. Now, the reason why we are interested in cascading multiple X310s is that, for example, if we want to sample the signal from multiple global navigation satellite system constellations, which are far apart, 1.2 gigahertz, 1.57 gigahertz, we cannot cover the full GNSS bands using a single SDR receiver. And we will have to focus each SDR receiver on one GNSS band. And nevertheless, if we want to have coherent measurements for time difference measurements, we do need to make sure that these various channels are indeed synchronous. Now, on the next slide, we are going to investigate what is happening if we can synchronize a B210 and an X310. So same story. On the left chart, already convinced that just without splitting the same reference clock, we are distributed plus or minus 15 nanoseconds within the sampling period, so there is no coherence between the channels. But on the right, we made X310 minus X310, B210 minus B210, so the two channels, and you see the difference. So your B210 has something like a standard deviation of about 100 picoseconds, the X310 something like picoseconds, so the difference is obvious, but still we are well below the sampling period. Now, these curves are all in the x-axis, what is happening within each acquisition, and the thickness of a line is the multiple repetition, the 1,000 times we repeat the experiment. If we now look on the next slide, the evolution of the mean value of a delay as a function of experiment index. So now you see that the x index has become 1,000, which is the experiment number, which lasted something like overnight 3 or 4 hours, because each measurement is about 10,000 long, 10 seconds long. Now you see the evolution in red of the time delay of the X310, in blue of the B210. And interestingly enough, on the next slide, we zoom in only on the X310 result, and you have this hindsight that there is some periodic event. Remember, on the x-axis, we're stopping the X310, restarting the measurement, stopping, restarting again, and yet there is some periodicity. This is an open question at the moment. I do not know what the source of this periodicity is, but it tells you basically here you see that the Y scale is 1 picosecond per graduation. So that gives you an idea of what can you get overnight in terms of synchronization between channels of an X310. Finally, to conclude on the next slide, I'm going to just investigate very quickly the Lime microsystem LMS 7002 fitted in the XTRX receiver. Again, if I just feed all channels of the X310 and the XTRX with my code and do not have some reference measurement, they are uniformly distributed in the sampling period of 200 nanoseconds. And indeed, if we go to the next slide, now what you see is that even if you make the difference between the two XTRX channels, these are the red curves, well, you see some drift. The x-axis is the measurement number, and it's going up to about 15 seconds. And what you see in the blue curve, the X310 has not moved by more than a picosecond within the 15-second acquisition. But you see that the XTRX has been drifting by up to 200 picoseconds during these 15-second measurements. I have no idea what's inside an LMS 7002. I have no idea how Lime microsystem architectured the receivers, but you do see that the samples are drifting between the two A to D converter, which is not happening on the analog device hardware and is not obviously happening with the FPGA sampling the data. So something here is shaky with XTRX LMS 7002 that needs to be investigated. So to conclude on the very last slide, the reason why I'm a bit concerned with this drift of the XTRX is that, well, this drift will limit your integration duration. If you're doing correlation, the longer the integration, the better the signal-to-noise ratio, or if you're doing GNSS measurements, you want to not be hindered by the motion of the satellite as you are detecting the code. And on the very bottom of this slide, you will see that 200 picosecond at 1.57 gigahertz of GPS-L1 is 110 degree of angular drift. So we're slowly getting a full phase rotation just because of the rotation of internal delay of the XTRX dual channel. Now, as usual, it's when you finish this work that you start reading the literature, and on the top left, you will find two papers published by NICT in Tokyo, where they actually did some YY, which is wireless interferometry measurement for fine time of flight measurement. They actually measure humidity using this. And what you see is actually they calibrated the N210, which is quite close to the X310, and they did find sub-picosecond standard deviation with 10 picosecond time delay resolution, which is in close agreement with our result as presented in this paper. With this conclusion, I thank you for your attention, and I'm open for any question you may have on this presentation. Thank you.
Wow. I'm impressed. I'm impressed because of a number of reasons. This research reminds me of some theoretical considerations about 15 years ago. No, was it? No, 10 years ago. Well, actually, I started 15 years ago in a project where I was investigating an N2P server that did a time jump, a time leap of a second. And I started in the project, started to think about what is a clock. And I read about a quote from what's his name? Daniel Mills, I think, the inventor of NTP, of the NTPD. And he said, well, a clock is a device that has an own independent perception of time. So an idea how quickly time is passing. The clock I was investigating wasn't a clock. It was a device made by a company called Black Box. In the end, it was a black box, but what it did was it was just receiving the GPS and it was just using the PPS signal, the pulse per second, in order to set the point of time in a controller. So, and when the telegram was, out of whatever reason, a little longer, so to speak, the beep, the reference, the PPS was kind of misadjusted, then sometimes it was just taking too long and it was just standing still for 1 more second. And once again, it was jumping a second to the future. So it was very unreliable because it was in a radar synchronization application, so very difficult. So, and then I thought, okay, can I build my own NTP server with a very small budget? And I had about 100 euros, and I took a Raspberry Pi and an arbitrary GPS module. And I thought, okay, well, I'm not such a super skilled engineer, and I haven't been working in the NTPD field for such a long time, and I would be absolutely glad to be precise at a millisecond level. And I was totally surprised when I understood that it's actually super easy not to be in the millisecond, but in the micro and possibly even in the nanosecond. Why is it so? Because a signal flies at the speed of light, which is 300,000 kilometers per second, which is 300 kilometers per millisecond, which is 300 meters per microsecond, and which is 30 centimeters per nanosecond. And since GPS is in the end a timing application that's able to give you a precision at about 3 to 4 to 5 meters, and for that reason, every cheap GPS chip that can deliver a positioning precision of about 3 to 5 meters will be able to give you a timing precision of about 10, 20 nanoseconds. So, and if you have a machine in the back end that's evaluating this PPS, the machine behind it is consequently about as precise as that signal. So this was my path into the nanosecond. And this is why I think that your research, dear Jean-Michel, is really fantastic. Because I understood, given the application, I mean, you're doing theoretical research, and I did something very practical, programming an NTPD. Okay, well, I wasn't programming it, I was configuring it with a very small budget. But I understood time control is something very interesting because it has a very strong lever. And there are a lot of things that rely on a very precise time control, such as stock market transactions or, well, radars. Everything that's related to radar, from civilian radars in cars up to military radars in missiles. So this is a very powerful technology if you're able to control the analysis of a signal down to the range of a nanosecond. So congratulations for your insights. Very astonishing. Very good. I have not been into such a deep research because I just have one USRP at home, and it's quite an old device, and 2 USRPs, and I don't have an octoclock, even though I did some experiments with a distribution amplifier recently. So I have a 4-fold output of 10 megahertz reference signal, but I do admit I didn't have the idea to compare them and to measure anything down there in the nanosecond range, which is pretty cool if you can do that. I cannot. But so I was just telling this to you, dear audience, because it's my practical approach to this field of research. And I would like to show you that even if you don't work in an institute like Jean-Michel does, there is a way for radio amateurs into this field. And it's interesting research. And well, if you have this analog signal coming into a device, it will still be, well, if you're using an SDR, it will still be transformed into the description of the signal. And yeah, well, this is then something where some kind of magic takes place. And I'm still not there where I can tell something about, okay, how to do the magic down in the nanosecond range and how to analyze a signal there. Well, I haven't been there, but you've done research there, and I find this really fantastic. So, dear audience, are there any questions? Have you been experimenting in the nanosecond range? Not yet. Nobody. Nobody's been experimenting in the nanosecond range. Do you have the means to experiment in the nanosecond range? What is the maximum speed of your oscilloscopes at home? Or in your institutes, wherever you work? Do you have a gigahertz oscilloscope? No? 5 oscilloscopes? 5 gigasamples per second. Yeah, well, then you're actually already somewhere there. So you have more or less the chance to see, well, a signal of, how much is that? What was it? A gigahertz? So that's interesting. Well, you have the Nyquist-Shannon theorem. You need a 2 gigasample oscilloscope to see a 1 gigahertz signal, right? Am I right? I think, well, maybe. So
what is fascinating here is that in a satellite ranging signal, you only have 5 megahertz bandwidth. 5 megahertz is the available channel. And yet we need to timestamp with 100 picoseconds. And you're not allowed to have a 5 gigahertz because you paid for the channel, and paying for 5 gigahertz would just be way beyond any budget. And so the reason why we went for this 5 megahertz bandwidth is the available bandwidth on the satellite. And yet we can measure with 100 picoseconds the time of flight. And as you just said, 100 picoseconds is 3 centimeters. Now you have to realize that you think a geostationary satellite is fixed in space, but it just keeps on being pulled away by everything, by the sun, by the moon, by tidal forces, everything. And the satellite is moving at 5 nanoseconds per second, which is basically a meter per second. And so you can get the satellite location within 3 centimeters using 5 megahertz bandwidth. So actually you don't need the full gigahertz. That's the amazing thing about pseudorandom sequence spread spectrum measurement.
You can't hear you. Just so long.
But you need to integrate over a quite long time to actually get that resolution, right?
In this particular case, it was 40 milliseconds.
Oh, that's quite fast, yeah.
You actually must have such a fast, because the satellite is moving at 5 nanoseconds per second, which over 40 milliseconds with already 200 picoseconds when you're integrating your code.
Okay, yeah, this is really cool research. So, any questions? Any more questions? No more questions? Well, okay, then this is late afternoon now. Jean-Michel, thank you very much for your talk. Fantastic, and thanks for quickly filling this gap. And